Hello everyone, welcome back to another video. Today we are going to get started with the M4 Trigonometry outcome. So before we get started, let's talk a little bit about what trigonometry is. It is just the study of the different properties of triangles. Really, we're just talking about finding out the different angles and the side lengths of triangles. Now, up until now, you guys have been talking mainly about triangles with right angles, and that's what we're going to focus on in this outcome. Only triangles where you have one 90-degree angle. Later on in other courses, you'll also talk about triangles that have three angles, none of which have a 90-degree angle in them. We want to talk first about something called similar triangles. Now, you may or may not remember much about similar triangles, but we call them similar triangles because they have the same ratio between corresponding sides of those triangles. So since those similar triangles will have the same angles, mathematicians back then quickly found out that for every specific angle in a triangle, there has to be a set ratio between those two sides. Now, again, that doesn't really mean a lot until I start to talk about some pictures, but in the meantime, we're just going to call those particular ratios our trigonometric ratios, or just our trig ratios for short. To start us off, we have three primary trig ratios. The first one being the tangent ratio, tan for short, the sine ratio, or sine without the e for short, it looks like sin, and the cosine ratio, which is symbolized by cos. Now, these ratios help explain the relationship between an angle and the two sides of a right triangle. We cannot stress that enough. We can only use those primary trig ratios for right-angled triangles, or right triangles. What that means for you guys is you don't need to stress about why it's called the tangent ratio or the sine ratio. I could call it the star ratio or the watermelon ratio. Again, it just happens to be a name that has been used conventionally. Now, in a right triangle, each side has some sort of name that's going to be dependent on the position of what we call a reference angle in this triangle. Now, the reference angle, we can think of it as which part of the triangle that you're looking at the rest of the triangle from. Now, in these two particular examples, we have our reference angle here and right here. For those of you who are wondering, what is that funny looking symbol that looks like a zero or an I with a line through it? So this is really just the Greek letter theta. And let me clean that up a little bit. So we pronounce this and spell it as theta. And we can think of that as just another variable like x or y or z. So typically in trigonometry, we use symbols like theta to help us explain, and more specifically in this case, a certain angle, or give a variable to an angle. Now let's talk about how we would label each side of the triangle. Well, I want to identify one side that will not change regardless of where your reference angle is, and that's going to be the hypotenuse in each case. So for the first and the second triangle, notice that your hypotenuse is going to stay in exactly the same place. Well, how do we figure out where that hypotenuse is? Remember that we're only dealing with triangles that have a single right angle. We can quite easily see where the right angle is in both of these. It's going to be right there in the bottom left corner. And the hypotenuse is always going to be directly across from the right angle. And your hypotenuse will always be the longest side. So you can write that down, always the longest side. So if you're trying to figure out the different sides of a triangle and you find out that your hypotenuse happens to be shorter than one or both of the other sides, you've probably done something wrong. So your hypotenuse will stay the same, and it doesn't matter where your reference angle is at any rate. So it's always, and for some reason it's not picking up, always the longest side. Now, starting with the triangle on the left-hand side, we're going to go and pretend that we're looking across at this side here. Now, this side of the triangle is what we call the opposite side because, you guessed it, it is opposite your reference angle. In the triangle on the right-hand side, if we're looking directly across, you can probably guess that this is now the opposite side. So notice how the opposite side has changed depending on where you are in the triangle. You can compare this similarly to if you're standing at the front of the room and you're looking at the back of the room. The opposite side of the room is going to be very different than if you were at the back of the room and you're looking towards the front of the room. Now, the last side of the triangle, we want to go ahead and look at the same side that the reference angle is on. So we're going to look and refer to the one that's closest to it, that is not the hypotenuse. And we can see here that in both cases, we have what we call the adjacent side. And really the word adjacent is just a fancy word that means beside, and really it just means beside your reference angle. Now here's a trick to figuring out how to label each side. If you want to memorize a type of order, I would always go for the hypotenuse first. That will never change. Then look for the opposite side, and then look for the adjacent side. That way, when you label all of your different triangles, you'll never mix up the different sides. The first ratio that we're going to talk about is the tangent ratio. And we typically express values of different ratios as fractions or decimals, not just for the tangent ratio, but also for the cosine or the sine ratio. And the tangent side happens to compare the lengths of the sides that are opposite and adjacent to whatever reference angle we have. So the formula for the tangent ratio is the tangent of A, which is just an angle, is equal to the ratio of the opposite over the adjacent side. So in this case, maybe I'll just write here that A happens to be some angle. Okay, it could be tangent of angle B, tangent of theta, tangent of C. Doesn't really matter. It's just kind of a placeholder. Tangent of A, and maybe I'll draw that arrow so that much better reflects that I'm just referring to angle A there. So if we're given this example, on the left-hand side, we have triangle ABC with the side lengths 6 and 2. If the tangent of angle A, we're going to be looking, first of all, at where angle A is, and it happens to be down here. So that means we're looking at the rest of the angle or rest of the triangle starting from angle A. So if we're looking directly across, and maybe what I'll do first is I'll find my hypotenuse. We know that our hypotenuse is going to be this side right here because it is directly across from my right angle. So I can call that my hypotenuse. We know that directly across from angle A is going to be what we call the opposite side. And then right beside your reference angle A is what we call our adjacent side. So we can go on to state that because we have tangent of A is equal to the opposite side over the adjacent side, my tangent of A happens to be 6 over 2. And we can further simplify that to give us tangent of A is equal to 3. So what does that mean for us? It really just means that in any similar triangle, your tan ratio will be the same, and your opposite side is going to be 3 times longer than the adjacent side. So really it just means if I were to draw another triangle here, and let's say that this is going to be 18 and this is 6, these two triangles are similar triangles. How come? Because the opposite side, if we're looking at my angle using this as my reference angle, if I'm looking directly across on my opposite side, comparing it to my adjacent side, 18 is 3 times as long as the length of 6. So since we're given triangle DEF, we want to try to figure out the ratio of the tangent of angle D and the tangent of angle F. So starting off with angle D, we can first note that our hypotenuse is going to be right here. And again, the hypotenuse isn't particularly important because we aren't dealing with the hypotenuse as a side length currently. Next, we're going to look at the side directly across, which is going to be my opposite side. And finally, my side that is right beside my reference angle, and that will be my adjacent side. Let's start off with our formula for tangent. We know that the tangent of angle D has to be equal to the opposite over the adjacent side. So we can state that tangent of D is equal to 3 divided by 4. So we can state that tangent of D is equal to 3 over 4, or we can state that the tangent of D is equal to 0.75, which is 3/4 converted into a decimal. Now let's quickly just copy that triangle over. Let's do this again. Our hypotenuse doesn't change, of course. It's going to stay, it's going to stay in the same place. So that's my hypotenuse. Now in this case, because we are looking at angle F as my reference angle, our opposite side is now down over here. So that's my opposite side. My 4 is now the opposite side. And my adjacent angle is now the side length 3. So once again, starting off with my tangent formula, tangent of F is equal to opposite over adjacent. In this case, tangent of F is equal to 4 over 3, or I can state that tangent of F is equal to 1.3 repeating. Example number 2 asks us to find the missing angles for triangle GHJ. So we can do a couple of different things. We can find one of these angles, so I can find either angle G and angle J, and we can use the triangle property that each triangle will always have the sum of its angles add up to 180 degrees. So again, if you forgot, we can show you how to do that very shortly here. So let's say we want to solve for angle G first. So again, that's my reference angle. We're going to first go ahead and look for my hypotenuse, and my hypotenuse will be directly across from my right angle. And we know it's the right angle because we can see that little right angle labeled there. So that's my hypotenuse. Directly across from angle G is my opposite side. And then right beside angle G is going to be my adjacent side. So once again, let's go ahead and start off with my formula. Tangent of angle G is equal to opposite over adjacent. And we can say that tangent of G is equal to 4 divided by 5. We can then convert that into a decimal if you'd like. So we can say tangent of G is equal to 0.8. But we're not quite done. We're being asked to find just angle G, but here we have the tangent of G. In mathematics, there are a lot of opposite operations. Addition and subtraction are opposite operations. Multiplication and division are opposite. Squaring and square rooting are opposite operations. In trigonometry, we also have opposite operations as well. So to get rid of this tangent in front, we have to use something called the inverse tangent function. Now what that'll look like when we apply that inverse tan function is it'll look like it's a tan to the power of -1. And what we want to do is we want to take the inverse tangent of that 0.8. Now how does that work out on your calculator? If we plug in, and maybe before you do that, make sure that your calculator is on degree mode. So if you have a TI graphing calculator, you want to hit the mode button right here. And you want to make sure that you go over to degree mode. I'm going to scroll down, go over to degree, hit enter, and then we can just hit clear to go back. So to find the inverse tangent function, you can see here we have just the regular tangent. So if I press that, we just get a tan. But I want the inverse tangent. So you can see up here, it looks like an inverse tangent. So it looks like a tan to the power of -1. So in order to get that, we want to hit second, then tangent. And we can type in 0.8 and just close that off with a bracket. And we end up getting 38.65. Let's round that up to 39. So what does that 39 mean? Well, that 39 really is just 39 degrees. Now, a lot of you are wondering, okay, well, we just punched something into the calculator. That doesn't mean anything. And you're right now it doesn't really. Now, the secret lies in this ratio of 4/5, or a ratio of 0.8. So all we're saying is that for any similar triangle where the opposite side is 80% the length of the adjacent side, your angle will always be 39 degrees. Now we're going to take a look at a chart, and this will age me a little bit, and this will bring some of your parents some fond memories as well. If we look at this tangent ratio chart, basically what this is, a lot of bright mathematicians over the years have compiled a list of those particular ratios and what angle is represented by each ratio. Now, our ratio in the last question happened to be 0.8. So all we're doing is we're seeing, okay, this is what ratio is representing a particular angle. So for our example, where our ratio is 0.8, we'd look down each column, and we're going to try to find a number very close to 0.8. Now, the closest one here to 0.8 happens to be 39. So we're saying that any triangle where the opposite angle is 80% of the side length of the adjacent side is always going to have an angle of 39 degrees. Let's go ahead and let's try that out for some of you guys who don't believe me. If I were to draw a triangle here, and this will be my right angle in the corner, let's call this angle A, and we want something that's 80%, so the opposite side here will be 8, the adjacent side will be 10. If I take the tangent of angle A is equal to 8/10, the opposite side over the adjacent side, we end up again with the same ratio, 0.8. And if we were to look up again that tangent ratio of 0.8, it would still correspond to an angle measure of 39 degrees. And we know that for any right angled triangle where that ratio is always true, we could go for 80/100, and that looks like 166. We've got 80 as my opposite side, if this was angle A, and this could be 100, we would still see that this angle here is 39 degrees. So really, all your calculator is doing when we're calculating the inverse tangent of 0.8 is your calculator is going into this chart that it has stored in its memory. It's saying, okay, which angle corresponds to a ratio of 0.8? In this case, it happens to be 39 degrees. And again, it wasn't exactly 39. It was a little bit in between. So really, we rounded to 39 degrees. So any ratio of the opposite over adjacent side of 0.8 will always refer to an angle of 39 degrees. So getting back to solving our original question of figuring out all of the unknown angles in this triangle, we can use the triangle property that all three angles need to add up to 180 degrees. That being said, if we take 180 degrees and we subtract h and we subtract g, this should give us angle J. So what you could do is we're going to take 180, we're going to subtract 90, we're going to subtract angle G, which we found was 39 degrees, and that should give us angle J. So at the end of the day, we end up getting 51 degrees is angle J. Alternatively, since we know we are working with a right angle triangle, the two other angles in the triangle need to both add up to 90 degrees. So we can actually start off with 90 degrees, and we can subtract our 39 degrees, giving us 51 degrees as well. Now, in the event that you don't start off with angle G, what we can do is we can take a look here at angle J really quickly. So if we start off with angle J, let's first go ahead and highlight this and label each of the sides appropriately. So this is our reference angle directly across, and I'll do that again in red, directly across from angle J is going to be my opposite side. My hypotenuse stays the same because, again, it is directly across from my right angle here in the corner. And then right beside my right angle, or not my right angle, my reference angle, is my adjacent side. So once again, let's start off with our formula. Tangent of angle J is equal to the opposite side over the adjacent side. So tangent of J is equal to 5 over 4. And if you'd like, we can simplify that or convert that into a fraction, which is 1.25. Now, before we move on to our graphing calculator here, let's write our last step that we'd need. And we want to get rid of this tangent here. So we would actually take the inverse tangent of both sides. So we'd actually have the inverse tangent of 1.25 would be equal to our angle J here. So let's switch on over to our graphing calculator. And again, if you don't have a graphing calculator, you can still do this outcome perfectly fine, but it is much easier for you to see exactly what type of inputs you've been putting into your graphing calculator if you have a nice large screen to see everything that's happened. So again, we're going to hit second tangent to get this inverse tangent on your screen, and we can put in 1.25. We're going to hit enter, and we're going to get 51.3 degrees. Now let's say you didn't convert that 5 quarters into 1.25. I can go ahead, inverse tangent, 5 divided by 4. Now the important part here is particularly if you don't have a graphing calculator, you want to make sure that you use those brackets appropriately. Notice I've ended off my bracket here, 5 divided by 4. So inside of the brackets is 1.25, and I hit enter, and I'll still get 51.3 degrees. So let's quickly round that to a whole number, which is 51 degrees. So we get angle J is equal to 51 degrees. Now that just matches up with what we found earlier. If we know that angle G was 39 degrees, we could figure out that angle J was 51 degrees using our triangle property of all three of those interior angles adding up to 180 degrees. Or we can start off with angle J, and we can go 90 minus 51 gives you the 39 degrees in this angle, or for this angle. And again, just because I do want to reference that tangent ratio chart, let's pop on over. Our ratio of the two sides or opposite over the adjacent side was 1.25. So if we quickly scroll and scan through our chart here, we'll notice that 1.25 is somewhere here in the middle. 1.25 is right in between, and it was in between 51 and 52 degrees, and we found that when we calculated it, it was 51.3, and we just rounded down to a 51 degree angle. So you can see how these charts are quite useful. And again, we don't use these charts anymore. They used to be found in the back of your math textbooks. Really, that's what your calculator is for now. But a cool bit of math knowledge for you. For this next example, it says the latitude of Fort Smith is approximately 60 degrees. The position of a solar panel should be close to its latitude. Is this design best for a house in Fort Smith? Now, a couple things before we get started. You might not know what a latitude is. If you recall, if we take a look at the Earth, as a giant sphere, and let me do my best impression of a sphere here. And we have some sort of sphere that looks like that. Your lines of latitude are really just east to west lines that circle the entire circumference of the Earth. And you see that red dotted line there. We can see that it goes around the entire globe. And we have our equator at 0 degrees. And we could have maybe, for example, this line of latitude here at 60 degrees. So it says the position of a solar panel should be close to its latitude. So even if you don't understand what a line of latitude is, we're going to go and refer to the latitude of Fort Smith being at 60 degrees. So if we want this solar panel to be close to the same latitude, really we're just looking for an answer that gives us something close to 60 degrees to figure out if it's a good design or not. So if we take a look at this triangle, and I'll outline it in red first. I did say red. So let's go ahead and do that. So we've got this triangle right there, and let me redraw it here so we can quickly give it some labels. We know that we have 9 feet here and 12 feet. And we know that we've got our solar panel along this blue side here. So let's label this the hypotenuse. And the question is, which angle are we looking at? Are we looking from this angle or this angle? Well, really, if we're thinking of this as your horizontal line, it wouldn't really make a lot of sense for us to be looking down from this angle and find some sort of measurement of the angle on this side. So we're going to start with the angle in this corner. And we can label the opposite side here. Let me do that in black, actually. So this side is going to be my opposite side. And this side will be my adjacent side. Now the reason, once again, that we're taking this angle is if this horizontal line were to be 0 degrees and we start to increase the angle by 1 degree, 2 degrees, 3 degrees, and so on, it would make much more sense for us to try to get closer to 60 degrees if we start from a horizontal line, otherwise known as your 0 degree position. So let's call this angle, let's call it angle A here in the corner. So we've got our opposite and your adjacent side. So our tangent of angle A, again, is equal to your opposite over your adjacent side. So tangent of A is equal to 9 over 12. Or if we simplify it, that's going to be 0.75. And if we take the inverse tangent of both sides, we get the inverse tan of 0.75. Let's go ahead and punch that into our graphing calculator. So second tangent, 0.75. And that's equal to about 37 degrees once we round up. So to answer the question that we were asked originally, is this design best for a house in Fort Smith? The answer is no. 37 degrees is not very close at all to that desired 60-degree angle. Here in example number 4, it reads, a 10-foot ladder leans against the side of a building with its base 4 feet from the wall. What angle to the nearest degree does the ladder make with the ground? So let's go ahead and draw this ladder here. And it's leaning against the side of the wall. We know that it's 10 feet long. So let's go ahead and label the ladder as 10 feet. And the base, or the bottom of the ladder, is 4 feet away from the wall. So we can label the bottom side of this triangle that we've now formed as 4 feet. What angle to the nearest degree does the ladder make with the ground? So we're looking from the ladder and the ground. So what we need to do is draw our angle right there. And the most confusing part about this question is probably making your diagram and then understanding exactly which angle we're looking at the rest of the triangle from. So setting up where your reference angle is in relation to the rest of the triangle. So we know that our right angle is going to be right there. This is our reference angle. Let's call this angle B just to change it up a little bit. I'm going to try to figure out what that angle is. So the first thing that I'm going to do is go ahead and label each of my sides. So again, directly opposite of my reference angle is my opposite side. Directly across from my from my right angle is my hypotenuse, which will be the 10 feet. And along the bottom here is going to be my adjacent side, which is right beside my reference angle. Now we do have a problem here. In order for us to figure out what angle B is, we need to identify what that opposite side is. So let's call that angle, or rather side X, side length of X. And we're going to have to go back to grade 9 to remember how to do this type of question. If we're trying to look for the side of a triangle, we need to look at the Pythagorean theorem. We know that a squared plus b squared is equal to c squared. So maybe I'll write at the top here, we need to use Pythagorean theorem. And we've got a squared plus b squared is equal to c squared. Now remember that the c squared, or really just the variable that's by itself, so when you have the sum of the squares of the other two sides is equal to the third side, this is going to represent your hypotenuse. So to follow proper triangle labeling rules, the side that's directly opposite from angle B is going to be my lowercase b. So maybe I'll do this in a different color so you can call this little b. So let's label the rest of the triangle here. Let's call this C and let's call this A. So this will be lowercase c and this will be lowercase a. So from here we've got 4 squared plus x squared is equal to 10 squared. Now I'm just pulling these numbers from my sides here. My value of a is 4, so I have 4 squared plus your b squared, which is just x squared, is equal to c squared, which is 10 squared. We can simplify this a little bit. 14 squared is 4 times 4, which is 16. So 16 plus x squared is equal to 10 times 10, which is 100. I'm going to subtract 16 from both sides, and I'll get x squared is equal to 84. We're going to punch into our calculators the square root of 84, and that gives us roughly 9.2 once we round up. So let's go ahead and put that label of 9.2 on the side. Now we can go ahead and continue on with the rest of the question here. So we want the tangent of angle B is equal to the opposite over the adjacent side. And we have now figured out that the opposite side of my triangle here, or from my reference angle, is my 9.2. So I've got 9.2 divided by my adjacent side, which was 4. So now this is where having a graphing calculator comes into handy, so you can see exactly what's happening. So I'm going to, instead of turning this into a decimal right off the bat, I'll take the inverse tangent of 9.2 divided by 4, and I'm going to put that into my graphing calculator. So we're going to go second tangent 9.2 divided by 4, close off my bracket, hit enter, and we end up with 66.5 degrees. Now we wanted our answer to the nearest degree, so 66.5 will round up to 67 degrees. So to answer our question, the ladder makes an angle of 67 degrees with the ground. So another useful tool for the tangent ratio is we can actually use tangent to help us find the side lengths of a triangle. Now remember from previous grades, we can solve proportions by cross multiplying. So if you want to solve these two examples, what we need to do is we're going to take the 3 here, we're going to cross multiply it with the x up here. And then we're going to take the 7 down here and cross multiply it with the 2. So we'll have 14 is equal to 3x. We're going to divide both sides by 3. And we end up with 14 over 3 is equal to x. Now, in the case of the second example where we don't have a clear denominator, what you could do is you could just divide it by 1, because 15 divided by 1 is still 15. Or because this is just a whole number, we only need to cross multiply one side. So I can cross multiply the y with 15. So we have 15y is equal to 60. Then we can divide both sides by 15. And we get y is equal to 4. So again, just to recap, our tangent ratio was the tangent of angle A is equal to the opposite over the adjacent side. What we're going to do is, if we're given an angle and we're given one other side, or one of these two sides, we can find out the opposite side or the adjacent side as well. So in these next few examples, we're going to use the tangent ratio to help us find an unknown side of a triangle. In this case, we're going to look for the length of RS to the nearest tenth of a unit, so to the nearest 1 decimal place. So if we take a look at our first one here, we have triangle SRT or RST, and we want to try to figure out this side length right here. So our first step, like always, is to identify where our reference angle is, and it's going to be the 35 degrees in this corner. And we're going to label the opposite side directly across from that angle. This will be my opposite side, that 15 centimeters. And since we are using the tangent ratio, and let's go ahead and rewrite it up here, tangent of A, or tangent of angle A is equal, let's clean that up, tangent of angle A is equal to the opposite side over the adjacent side. So like always, I know that my hypotenuse is directly across from my right angle, which is right here, so directly across. So that means that side RS is actually my adjacent side. And since I don't know what that side is, let's call that x. Starting from our formula, tangent of A is equal to the opposite over the adjacent side. We know what tangent of, and in this case, not tangent of angle A, in this case, tangent of S. So actually, let's go ahead and substitute that S there. So we know angle S is equal to 35. So we'll put tan of 35 is equal to my opposite side, which is 15, divided by my adjacent side. In this case, it's x. So we're going to have to use proportions to help us solve for x here. Now again, because we have just our one denominator here, we can pretend that this is divided by 1, and we can do this. So this is our first option. We can divide this by 1, and then we can cross multiply with these two. So we can cross multiply those two, and then we can cross multiply those two. Or what we can do instead is, if we want a bit of a shortcut, since we only need to worry about this denominator, we can imagine that we're multiplying both the right-hand side and the left-hand side by x. So all I need to do is multiply those two together, and I get x times the tangent of 35 is equal to 15. Now again, tangent of 35, if I were to punch that into my calculator, Now, tangent of 35, if I were to punch that into my calculator, tangent of 35, all it does is it gives us a ratio. So the tangent of 35 degrees gives us a ratio of 0.7. Okay, and again, if I were to go back to my chart and I look at an angle of 35 degrees, we can see that an angle of 35 degrees has a ratio of the opposite over the adjacent side of 0.7. So that's what that number is telling us. So if I were to refer back to this, we can pretend that that tangent of 35 is just a number. I could just as easily have x times 5. Obviously, it's not 5, but that's really all we're doing there. So the reason why I bring that up is because we want to get that x by itself. I can now divide the left-hand side by the tangent of 35, and I can divide the right-hand side by the tangent of 35. So here I'm left with x is equal to 15 divided by the tangent of 35. And if I were to plug that into my calculator, let's see what I get. 15 divided by the tangent of 35, and let's close off that bracket. We end up with 21.4. So if we were to round that answer to the nearest tenth of a unit or the nearest tenth of a decimal place, we get x is equal to 21.4 centimeters. Our next question, we're going to look at, again, the side length of RS. So in this case, that side right there. And we are going to start off with our reference angle, which is right here, angle T. So that means that my opposite side will be right here. And let's call that X. My hypotenuse is over here because it's directly across from my right angle. And the 24 inches then has to represent my adjacent side. So again, depending on what you'd like to do first, you can label the hypotenuse first, then the opposite side, depending on where your reference angle is, and then finally your adjacent side. I find that to be the simplest way of labeling for most students. So let's start off with our tangent ratio. So tangent, instead of A, we actually are working with tangent of T is equal to opposite over the adjacent side. So tangent of 48 is equal to the opposite side, which is X, divided by my adjacent side, which is 24. Again, because we only have the one denominator here, what I can do is we can work through it like this. Let's go ahead and cross multiply these two. And I'm a little tight on room here. So you've got 24 times the tangent of 48 is equal to x. So if I plug that into my graphing calculator, 24 times the tangent of 48, that gives me 26.65. If I were to round this to the nearest tenth, this 5 will turn that into a 7, so 26.7. So 26.7 centimeters, 26.7 centimeters is equal to x. For question C, let's go ahead and label or figure out where our reference angle is. So right there in the corner, directly across from it is my opposite side. Let's call this x. My hypotenuse is over here. And finally, my adjacent side is that 25 centimeters. So starting off with my formula, tangent of t is equal to opposite over adjacent. So we get tangent of 15 is equal to my opposite, which is x. Do that in red, x divided by my adjacent side, which is 25. We are going to cross multiply, or we can really just get rid of the denominator there. So we'll multiply those two together. And we end up with 25 times the tangent of 15 is equal to x. So let's plug that into our graphing calculator. 25 times the tangent of 15. And that gives me 6.7 once I round it. So 6.7 centimeters is equal to x, or x is equal to 6.7 centimeters. Last one here on this page, we're going to look for that side length there. So let's start off with our reference angle, which is the 31 degrees. And let's do that in red. Directly across is my opposite side. My hypotenuse is here. And my adjacent side, let's call that x. Let's start with our formula. Tangent of s is equal to the opposite side over the adjacent side. So tangent of 31 is equal to my opposite side, which is 403, divided by my adjacent side, which is x. We're going to cross multiply these to get rid of the denominator on the right-hand side. So we get x multiplied by the tangent of 31 is equal to 403. Let's divide both sides by tangent of 31. Remember, tangent of 31 just gives us a ratio for that angle of 31 degrees, and it's just the number. So if it helps you out, dividing by tangent of some number, so tangent of 20 will just give you a number. We could pretend it's 5. So it's just like dividing both sides by 5. We're not dividing by letters, okay? That's one of the biggest misconceptions I get from students. How do I divide by t, a, and n at the same time? We're not. We're dividing by a ratio. So when that's all said and done, we get x is equal to 403 divided by the tangent of 31. So 403 divided by the tangent of 31 gives us 670.7. And this one happens to be in millimeters. So let's try out a word problem. It reads out, a searchlight shines vertically on a cloud at a horizontal distance of 250 meters from the searchlight. The angle between the ground and the line of sight is 75 degrees. Determine the height of the cloud to the nearest meter. Now, this question is made a little simpler by the fact that they've provided us with a picture. The tough part of this is if you weren't given a picture, it'd be the drawing itself. And after you've completed the drawing, it's a fairly straightforward problem. Now, if we take a look, we're given our 75 degrees down here in this corner. The searchlight goes straight up, and here is your line of sight if you're here looking up directly at the bottom of the cloud there. So you want to try to figure out the height of the cloud to the nearest meter. If we're looking at the height of the cloud, we'd measure straight up and down vertically, so we'd have to go from here to here. So let's draw our own triangle here. And we can label these with our own letters to make it a little bit simpler for ourselves. So we have triangle A, B, and C. And again, it doesn't really matter how you label it. It's really up to you. You end up changing the different sides afterwards, or the different labels. So you know this is 75 degrees. So we're going to go ahead and label each part of our triangle. We know that this is the hypotenuse because my right angle is here. So directly across from it is my hypotenuse. Directly across from my reference angle of 75 degrees is my opposite side. So let's call this H because we're looking for the height there. And then finally, this bottom side is going to be my adjacent side. Now we definitely need one more side. I'm not too worried about the hypotenuse because the tangent ratio only deals with the opposite and adjacent side. So our goal here is to figure out what is the length of my adjacent side. Now from the question, it reads, a searchlight shines vertically on a cloud at a horizontal distance of 250 meters from the searchlight. So if the searchlight is here and the horizontal distance of 250 meters is going to represent the bottom here, and then we can write that our adjacent side is equal to 250 meters. So let's set up our ratio. Tangent of angle C is equal to opposite over my adjacent side. So the tangent of 75 degrees is equal to the opposite side, which is h, divided by my adjacent side, which is 250. Now again, because we are trying to get rid of the denominator on the right-hand side, we can multiply both sides by 250 to get rid of the 250 on the right. And we end up with 250 multiplied by the tangent of 75 will give me my height. So let's plug that into my calculator. So 250 times the tangent of 75 gives me a grand total of 933. So in this case, 933 meters is my height. And again, get into a really good habit of writing out a sentence to solve each of your word problems. So the height of the cloud is 933 meters. So that's it for part 1 of the lesson for the M4 trigonometry outcome. Hopefully I haven't scared you guys off with all this talk of triangles. In the next lesson, we're going to talk a little bit more about the tangent law as well as the sine and the cosine law. And then we're going to try to figure out how to solve for all different angles and sides of the same triangle and explore a couple of word problems associated with each of those. Hope you guys enjoyed the lesson. I'll see you guys in the next video.